RAMSEY theory, named after the British mathematician and philosopher Frank P. Ramsey, is a branch of mathematics that studies the conditions under which order must appear. Problems in RAMSEY theory typically ask a question of the form, how many elements of some structure must there be to guarantee that a particular property will hold? A typical result in RAMSEY theory starts with some mathematical structure that is then cut into pieces. How big must the original structure be in order to ensure that at least one of the pieces has a given interesting property? This idea can be defined as partition regularity. For example, consider a complete graph of order n. That is, there are n vertices and each vertex is connected to every other vertex by an edge. A complete graph of order 3 is called a triangle. Now color every edge red or blue. How large must n be in order to ensure that there is either a blue triangle or a red triangle? It turns out that the answer is 6. See the article on Ramsey's theorem for a rigorous proof. Another way to express this result is as follows. At any party with at least 6 people, there are 3 people who are all either mutual acquaintances, each one knows the other 2, or mutual strangers, each one does not know either of the other 2. See theorem on friends and strangers. This also is a special case of Ramsey's theorem, which says that for any given integer c, any given integers n1, nc, there is a number, r n1, nc, such that if the edges of a complete graph of order r n1, nc are colored with c different colors, then for some I between 1 and c, it must contain a complete subgraph of order n whose edges are all color I. The special case above has c equals 2 and n1 equals n2 equals 3. 2 key theorems of Ramsey theory are 1. Van der Waerden's theorem, for any given c and n, there is a number v, such that if v consecutive numbers are colored with c different colors, then it must contain an arithmetic progression of length n whose elements are all the same color. 2. Hill's-Jewett theorem, for any given n and c, there is a number h such that if the cells of h-dimensional n times n times n times n cube are colored with c colors, there must be one row, column, etc. of length n all of whose cells are the same color. That is, a multiplayer n in a row tic-tac-toe cannot end in a draw, no matter how large n is, and no matter how many people are playing, if you play on a board with sufficiently many dimensions. Hill's-Jewett theorem implies Van der Waerden's theorem. A theorem similar to Van der Waerden's theorem is Schur's theorem. For any given c there is a number n such that if the numbers 1, 2, n are colored with c different colors, then there must be a pair of integers x, y such that x, y, and x plus y are all the same color. Many generalizations of this theorem exist, including Rodau's theorem, Rado-Folkman-Sanders theorem, Hindman's theorem, and the Millikan-Taylor theorem. A classic reference for these and many other results in Ramsey theory is Graham, Rothschild and Spencer. Results in Ramsey theory typically have 2 primary characteristics. Firstly, they are non-constructive. They may show that some structure exists, but they give no process for finding this structure other than brute force search. For instance, the pigeonhole principle is of this form. Secondly, while Ramsey theory results do say that sufficiently large objects must necessarily contain a given structure, often the proof of these results requires these objects to be enormously large, bounds that grow exponentially, or even as fast as the Ackermann function are not uncommon. In many cases these bounds are artifacts of the proof, and it is not known whether they can be substantially improved. In other cases it is known that any bound must be extraordinarily large, sometimes even greater than any primitive recursive function. See the Paris-Harrington theorem for an example. Graham's number, one of the largest numbers ever used in serious mathematical proof, is an upper bound for a problem related to Ramsey theory. Theorems in Ramsey theory are generally one of the 2 types. Many theorems, which are modeled after Ramsey's theorem itself, assert that in every partition of a large structured object, one of the classes necessarily contains a large structured subobject, but give no information about which class this is. Occasionally, the reason behind such Ramsey-type results is that the largest partition class always contains a desired substructure. The results of this kind are called either density results or Tarrant-type results, after Tarrant's theorem. Notable examples include Chemin-Rady's theorem, which is such a strengthening of van der Waarden's theorem, and the density version of Hill's Jua theorem.